like for example on the final. So I explained this before, that the final is not just going to be programming and algorithms, it's also going to be conceptual questions on all of the things that you program. So you need to theoretically understand what linear interpolation is and how it works and what it's used for. The second thing that we did and that we do in every single one of these topics at the end is we use the intrinsic functions associated with the topic. So for this, it was mostly interp 1. And then the last thing that you did in the lab was you wrote an interpolation algorithm. And the majority of the interpolation algorithm comes from finding the window. So locating the 2 points that bracket your point, and that requires the for loop with the if statement. It's actually not a new algorithm, it's just a find algorithm. We've already written several of them in 2 other labs. But it's a for loop that runs through all the points and an if statement that has the condition that you're looking for. So those are the 3 parts of interpolation that you should have learned, or that you are currently learning. So this is something that I always see around this time. I have literally no idea why. I don't know how to fix this. I feel like I say this so much. But everyone always forgets the 1 colon in the syntax for a for loop. It's like the number 1 thing that I see wrong in for loops is just putting 1 number. So remember, if you say I equals length of x is a number, say 10, which means your loop runs once for I equals 10, just 1 time. But remember that for loop structures work by running the loop for every index in the array on the right side of 4. So a lot of people intuitively want the for loop to run the number that you put next to I. So if I say I equals 10, they want the loop to run 10 times. But that's not how the syntax in MATLAB works. The syntax works by putting an array and it running for every element of the array. I've taught you guys to just do a standard 1 colon 10, 1 colon length of x, but you could put any array there. You could put any array you want and it will just run for every element in that array. But intuitively it makes the most sense to just use it as your index and do 1 colon 10. It will run for 1, 2, 3, 4, all the way up to 10. Okay, so just don't forget that. I'm going to move over to the .cam now. Most of what I'm going to be doing today is in the .cam, but I'm going to show you a few things in MATLAB as well with the linear interpolation. What did I just say? Yeah, I hear that I just said that, but yeah, I meant that. You want to go over it again? Okay. So I'm going to start by just explaining, why does this do this every time, guys? It's actually not working this time. Oh, I should have said yes. Okay, I'm just gonna try one more time. This is fun, right? It's great. Okay, so I started this topic last semester. Was the first time I incorporated it into 203, or this programming class, because I've taught this at other universities. Because your program does not have a linear algebra course. Most engineering programs, it's part of the curriculum, linear algebra, and you guys don't have that. It's not a required math course, but it's one of the most important math things that you need. So what we're trying to do is incorporate it in other courses instead of having, because we don't have enough credits basically right now for you to take a full math course with the way the curriculum is currently. So you're seeing it a little bit here. You're going to see it a little bit more in 303. And so that's what I'm telling you this because there was a lot of feedback last year that was like, why are you making us do something that we've never done before? And I'm like, hello, this is school. Like, you're here to learn new things. You know what I mean? So, like, I'm here to teach you the basics of linear algebra right now. That's what this topic is for. And then you're going to continue to be exposed to it. But guess what? You've done lots of linear algebra because you took algebra in, like, 2nd grade, right? When do you start that? Like, around then, right? And then you take it again in middle school, and then you take it again in high school. So this is just more algebra. Algebra is, by far, always going to be in your life. I mean, for most of you. I love algebra. So what we're doing in this topic is we're kind of defining linear algebra to some sense, because we're not just solving 2 equations and 2 unknowns. We're trying to look at it in a more general sense to be able to solve any system of equations. But can I tell you a secret about engineering? Literally all you do in every single class is set up systems of equations, make sure you have enough equations, enough unknowns, and solve them. Like literally every single class you take. And if you can just get that in your brain, that you just need to have the same number of equations as unknowns to close any engineering problem, that's like 75% of the battle of the problem. Physics, that's the easy part. So what we do in this sort of like topic is we're going to talk generally about systems of equations. And so when you take a linear algebra course, the equations are written in general using this exact notation. It's the same every single time. So your first equation will have n number of unknowns. So the first unknown is x1, the second unknown is x2, and then the last unknown is going to be xn. And then you use this this notation for numbering the coefficients because it matches with how you're going to set up your matrix. But a11 is the first coefficient, a12 is the second, and then a1n is the last one. So this has n unknowns. So if you wanted to solve for all of your unknowns, linear algebra says that you need to have n equations. So you're going to need to set up another equation, and you're going to need to number or put in order the unknowns the same way that you put them in the first equation. So you can imagine this as x, y, z, or r, s, t, any unknowns that you're looking for in any system. And you're just going to use this numbering system where you change the coefficient by columns and numbers the same way you would with if it were in a matrix. And then everything that's not multiplied by one of your unknowns goes on the right-hand side of the equation. So those would be all of your knowns. And you'll just number those generally as b. That's what's just used for all linear algebra systems. So in order to close or solve for all of your unknowns in any system of linear equations, you're going to need to have the same number of equations as you have unknowns. And so putting the n in front of this last set of coefficients means that it's the nth equation. So we're going to write out this last one. But if you had 2 unknowns, you would have 2 equations. If you had 3 unknowns, you'd have 3 equations. Now, I spent a large majority of my high school career solving these equations on my graphing calculator, and let me tell you, if I could brag about one thing in my life, it's the most proudest moment. I could program the matrices so fast and get the solution. And I was so good at it, and it never has provided me any use ever since then. But no one else does that. But we did this all the time in high school, where we set up our system of equations into matrices and we solved for them. But it sounds like that is not a consistent thing that was done in everyone's high school, so that's what I'm going to show you about today. So I'm going to refer back to the same notation. So ij, those are all constant coefficients. So like numbers, like 2, 3.7, 4.1, -5. Those are examples of constant coefficients. X of I, those are the unknowns. That's usually what you're trying to solve for by setting up the equation. BI's, those are all your knowns, and they're all constants, so they don't depend on any other x value. And N is the number of equations and number of unknowns. So again, they must be the same if you want to solve for them. So what I'm going to do is I'm going to start by just showing you how to convert a system of equations into matrices, and then I'm going to review a little bit of matrix math depending on what you've seen before. So I'm going to give you an example for this one of a system of 3 equations and 3 unknowns, and then I'm going to convert it into matrices. Again, this could be painfully obvious and review for you, or this could be completely new to you. So I welcome wherever that is for you, but it's not too bad. So here's my first equation, here's my second equation, and then my final equation. And I'm going to write this so that my unknowns are grouped so you can see how the matrix is set up a little bit easier. So if we convert this to matrix form, all you do is you take all of your coefficients and you place them in a 3x3 matrix, and you're going to group them exactly how I just wrote them. So the first column is for your first unknown, your second column is for your second unknown, and your third column is for your third unknown. So basically, if you're familiar with matrix algebra, which I'll review in a second if you're not, and you can look back at this if this does not make sense to you after I show you the matrix algebra. If you multiply this row by this column using matrix algebra, you're going to take 3 times x1 plus 2 times x2 plus 1 times x3, and you can see that gets you the left-hand side of the equation, and that's how matrix algebra works. And then you're going to set it equal to 2 on the other side of the equation. And then to fill in the rest, you're just going to fill in the coefficients along the rows, and then fill in the b's on the column on the right-hand side. And the way that matrix algebra works is you take the first row, multiply it by the first column, and it equals the first row. The second row multiplied by the second column, and that's going to equal the second row, etc. And you can see that it'll just match exactly the equation. So what we do is the standard is to call that first matrix that has all your coefficients, that's called A typically, and it's a matrix, so it has 2 dimensions. We call the unknown array or vector X, and typically there's some sort of vector bar over it to indicate that it's a 1D. And then the all of the constant coefficients that don't get multiplied by an unknown are thrown into the B with the vector over it. If you ever see this in a textbook, usually this is bolded to indicate that it's a matrix. Sometimes people write 2 bars over it, but it's all just syntax. So that means that if you wanted to rewrite this matrix equation without writing out the matrices, you just write AX equals B. So we can do that same thing with a general matrix, and then our matrix will just be based off of general coefficients. So if I want to just do the 3 by 3, I'll have A11x1 plus A12x2 plus A13x3 equals B1. And then the second equation is A21x1 plus A22x2 plus A23x3 equals B3. And then the third equation is A31x1 plus A32x2 plus A33x3. Equals B3. And I'm writing it that way because then when you write out a method, you can write it for any general coefficient, any general B, and then you can apply it to any system of equation rather than writing it out for this particular system. So your matrix is going to look exactly the same, except for your coefficients are going to be, and you'll notice they're numbered exactly the way that MATLAB numbers them. Because MATLAB, what does it stand for? Matrix Laboratory. So it's set up to be able to do this easily and well and fast. So when I show you the method that you're going to be using to write your lab code, I'm going to be referring to this general form of a system of linear equations, the AX equals B. So what I wanted to show you really quickly, in case you haven't done much with matrix algebra, is there's a lot of rules for how matrix algebra works versus regular algebra, but in order to do what we're doing, you don't really need to know very much of it, so I'm just going to show you the one thing that you have to understand, which is how to do matrix multiplication. And I want you to know how to do it on paper, like what that means, like what the dimensions, how they work out, and then I want you to know how to do it in MATLAB. So let's say that A is a 3 by 2. I'm going to give you some numbers so I can show it to you in MATLAB. So 318604. This is a 3 by 2 matrix. And B, it's going to be matrix multiplied by a 5, 9, 7, 2, 2 by 2 matrix. So can anyone tell me what the dimensions of the matrix multiplication is going to be? Does anyone know or remember? It's going to be 3 by 2. So your inner dimensions always have to match, and then your result will always be whatever was left over, so 3 by 2. So you're going to just take the first row and multiply it by the first column. And all that you do is 3 times 5 plus 1 times 7. So that is 22. And then you're going to do the first row by the second column, and that comes out to 29. So that's 3 times 9 plus 1 times 2. And then you're going to do the second row times the first column, and that's going to be 8 times 5 plus 6 times 7, and that comes out to 82. And then the second row times the second column, which is 84, and that pattern just continues, and it results in a 3 by 2.
So it's 3 times 5 plus 1 times 7.
No, 3 times 5, oh yeah, times 1 times 7. So you do the first row by the first column, and that goes in the first spot. The first row by the second column goes in the second spot. The second row by the first column goes in the second spot. So you can kind of like work through that and just make sure that all that makes sense. In MATLAB, how you do this is the whole dot thing. always told you that you just always put the dot there. If you don't put the dot, this is what MATLAB does. This is what not having the dot operator does. So if I define that first array, 3, 1, 8, 6, and then 0, 4, that's A. And then B is a 2 by 2, 5, 9, 7, 2. And then if you just put A times B and you don't put any dot there, it's going to do matrix multiplication. And you do it because that's how you solve systems of linear equations, basically. And that's why you always get those errors on dimensions don't agree and stuff, because the dimension mismatch is totally different when you're doing matrix multiplication versus element by element multiplication. So what I'm going to be talking about is 3 methods. Yeah. So I'm going to show you 3 methods for solving systems of linear algebraic equations, and 2 of them are going to be very straightforward, and we're not going to be writing the algorithms for them because they're already available in MATLAB. So one is the inverting matrix method. The second one is an elimination method. There's actually quite a few, and there's quite a few available in MATLAB. This is a method that you've probably already used before. This would be like row reduction, Gauss elimination, Gauss-Jordan. If you've ever used any of those are all elimination methods. The other one is LU decomposition, you might have heard of. So these 2 methods are direct methods. So they're basically just doing algebra is the way you could think of it, eliminating unknowns and substituting in and backwards substituting to get all of your unknowns. And you know how to do that. If you have 2 equations and 2 unknowns, everyone knows that you just solve for one unknown, plug it into the other one to take away one of the unknowns, and then plug it back in, right? So you do that basic thing, but you just do it with more equations and more unknowns for these direct methods. The one that you're going to be programming is called an iterative method. And it's basically that you guess and check. So you guess a solution and you check it, and if it's not right, you guess it again, but do it better. And people think that's insane, but that is the only way large systems of equations are solved in any real engineering model or solver. It is completely impossible to use these direct methods on real engineering problems because you're trying to invert or solve for millions of unknowns at a time, and so we don't have the computational resources to do it. So let's go over inverting first. This is the most expensive method, meaning that it takes the most computations for the computer to do it. Expensive means computationally expensive. So in computations, we call a computation or an algebraic manipulation a flop. Have you guys ever heard that term before? It stands for floating point operation. So if you multiply 2 things by each other, that's called a flop. So inverting a matrix takes the most flops by the computer, so it's the most expensive. So the way that you solve this by inverting is if you multiply both sides of the equation by the inverse of A. And again, if you are not familiar with matrix algebra, I recommend that you review it in the textbook. But multiplying a matrix by its inverse, does anyone know what that gets you? The identity matrix, which is just a bunch of 1s and 0s. And the identity matrix just is like 1. It's like the equivalent of 1 in a matrix. So it's equivalent to just having x. So this is another feature of matrix algebra that's different than regular algebra. You can't do division, you have to do multiply both sides by the inverse. And that's something you would learn in an algebra class. So in MATLAB, this is very easy to do. If you set up your coefficient matrix A, like I just showed you by just putting all the coefficients in, and you set up your B matrix, you can simply type INV of A, matrix multiply B, and it solves a system of equations. So if you're ever doing homework and you have to solve some system of equations that's more than 3 or more, this is the easiest way to solve it. There are a couple other ways to do this in MATLAB. The first one is something called the backslash operator, and it's actually, let me talk about that in a second. You have a question?
Yeah, you said INV when you're speaking, but you wrote down, is that INX?
INV. It's inverse, the inverse operator. Yeah, so it's the same as I, or A raised to the -1 power. And so if you've never inverted a matrix or you've never done anything with matrices, it takes a lot of operations to invert a matrix. And so if it's a 3 by 3, it takes about 8 operations. I forget, but it's close to the order of the system. So if it's 3, I think it might be 3 squared. But anyways, it's a lot. Do you have a question?
Yeah, so you can write it as inverse, but can't you also write it as A with
Okay, so the elimination method is the second method, and so let me just give you a few of those names. So this was something we programmed last year that we're not programming this year because all of them are provided in the, okay, because it's too hard. That's why we didn't do it. So Gauss elimination is one method, and that's row reduction. So if you've ever done row reduction on your calculator, it's probably closest to Gauss elimination, but it's basically reducing your number of unknowns and then backward substituting. That's all it is. And so in MATLAB, the way that you do that is actually programmed in as an operator, which is really cool, and it's relatively new, and that's what the backslash operator does. The result is the same. They both solve the system of equations, but this takes slightly less operations, and so if you do the inverse A times B, MATLAB will give you a warning and tell you to do this because they do the same thing, but one of them is more efficient. The other option for, again, doing the same thing is a function called linsolve. So that's L-I-N solve. And it just is a function that takes your two inputs A and B, and it also solves it, but it uses a different method called LU decomposition. And Gauss elimination and LU decomposition are the same expense. Like, they take the same amount of flops. They're just different methods. In a numerical methods class in many engineering programs, these would be 2 of the things that you would program in the methods class. Any questions about that? So I'm not going to go over the algorithms from it all because we're not doing them, but they actually, I think they're in your textbook if you're curious how those algorithms work. So again, those methods are great. They're easy to use, but they're completely useless in any real engineering system. So while it's going to seem weird that we are programming this iterative method when all of the problems that we're solving can be solved using these simpler methods for comparison, I'm showing you this method because this is realistically how all systems are solved, and this is the algorithm that's used. So we're going to be using the same set of equations that I wrote up before with the coefficients. So given the 3 by 3 system is what I'll show you just for simplicity. And I already wrote out what those coefficients are, A11, A12, etc. What an iterative method does is it's basically 2 steps. One is you take all of your equations. So in this case, we're thinking about 3 equations. In your code, I think you have 7 or 8 or something, but it's not any different to do it for more. And you're going to take each of those equations and solve for one of the unknowns. So we're going to take the first equation and we're going to solve for the first unknown. So if you go back in your notes and look, you are just going to solve for x1, and then everything else will be left over on the right-hand side. So again, I'm just taking this system right here, taking the first equation and solving for the first unknown. And then you take the second equation and solve for the second unknown.
With the inverting matrix, is that, so we don't use division in that case, but we can use division in this case?
Well, this is now just algebra, because I'm taking one equation and just solving for it. So this is no longer matrix algebra, because I'm doing the algebra on individual equations. But yeah, if you were going to do this on the whole set of equations at once, you would need to do that. And then I'm going to take the third equation and solve for the final unknown. This is cool, right? This is awesome. This is excellent. So what we're doing now is iterative methods. And by the way, iterative methods are used all the time in engineering. Like, we learn all this math and then we just guess and check. You know what I mean? But all you're going to do is you're going to say, I'm going to guess an x1, an x2, and an x3. It's not going to be right because we're guessing it and we have no idea what we're doing. And then you're going to put those guesses into the right-hand side of all of three of these equations. And we're going to get a better x1, x2, x3 based off of those guesses. And that's still probably not going to be very good, right? Because that was just a guess and then an update based off the equations. So then we're going to take the new x1, x2, x3. We're going to plug it again into the right-hand side and get new x1, x2, x3. And we're just going to keep doing that until it stops changing, until x1, x2, and x3 stop changing. And once they stop changing, then obviously they're the solution to the equation, right? Because they're solving the equation. It's kind of crazy, but that's all you have to do to solve a system of equations. So if you have a dumb computer that can do a lot of repetitive things, that's a really great way to do linear algebra. And why it's good is because when we actually use this in modeling codes, think about like an engineering system that has like a fluid in it, and you're solving the fluid through time. The fluid isn't changing that much from time to time. So we have really good guesses for our system. We're not just guessing anything. We have pretty close guesses. And then we're just iterating to make sure it's good enough, and then we're moving on. And so that's why iterative methods are so nice. So the second step of this algorithm is to just repeat those definitions for each variable until x1, x2, x3 stop changing. So how do we do that? This is something that is so important for all engineering codes. It's used all the time, and it's called a residual. So you know what it means for them to stop changing, but how do you set that up in your code? What you're going to want to do is take your x values, and I'm going to put an I here because I want to check all the x values, and so I just means however many unknowns, you're going to check all of them. And I'm just going to compare the latest guess, the one that was most recently updated, with the one before it. And when you guys worked on that lab with the population, you did this where you saved the old population at the top of the loop. That's what you're going to do here too, is save the last x that you guessed, compare it to the new one, and basically when that's small enough, and this is like a huge computational thing that you got to start thinking about, small enough doesn't mean 0 for computers, because zero doesn't exist in a computer. There's truncation error, and so computers, 0 is like, your computers is probably like 10 to the minus 30 or something. So that would be the best you could get, but like we don't even need that. So just started off at like 10 to the minus 3, just like not very close to 0, but you can start it off there, and then once you get your code working, you can decrease epsilon to make it better and better, and then it will just keep iterating more to more precision. And sometimes it helps to normalize depending on the magnitude of your unknowns. Like if they're really big unknowns, you can normalize by the magnitude, but the error is all you really need, and it'll just help you keep track of like where you are. So dividing by one of them, the old or the new, will just get it to be around 1, basically. So this is the algorithm for a 3 by 3. Yours is a 7 by 7 or 8 by 8 or something, but the challenge of the lab is to write this in general for any number of equations, any unknowns. It would literally take you about 5 minutes to write this for 3 equations, 3 unknowns. And if you want to be good with that, go for it, but it is going to be more challenging to move forward in some of the other things that you're going to be doing. So the goal is to generalize this so that you can do this for any number of equations, any number of unknowns. So that's the challenge of the lab. So what I would recommend is you first program it if this is overwhelming for you. Some people like just go in and attack this. They're so excited to generalize it. Go for it if that's you. But if it's overwhelming to think about this algorithm, you're just going to put in a while loop with this condition, put these 3 lines in there, just iterate. You know, it's pretty straightforward. You got to think about accessing, you got to think about updating, but otherwise it's fine. What I want to end with is talking a little bit about cost. So I have spoken to this a few different times, what cost means and what flops mean, but I want you to actually understand what it is. So let's first define what a flop is. So a flop is a floating point operation. And it's just a way to define what kind of things the computer is doing. So if the computer adds 2 numbers, that's a flop. If the computer multiplies 2 numbers, that's a flop. And it's called floating point because remember the default number type in MATLAB is a 64-bit floating point number. So if we want to compare the 3 methods that I've talked about, the inverse method requires 3n cubed over 3 flops. And remember, n is the number of equations or number of unknowns. So help me do the math here. If we had 3 equations, what's 3 cubed? 3 cubed is 9, 27. Is that right? Help me.
Yes.
Which is 54 divided by 3 is like 16. Is that right? No, 18. 18 flops. If anyone just followed that for 3 equations, 3 unknowns. Did I do that algebra wrong? 54 divided by 3? Oh, it's 4 times 27. Got it. It's 108, so it's actually 36 flops. Maybe. Who knows? But it's something like that. So that's what that means. It's just however many equations cubed times 4 over 3. That's the inverse. The elimination method, the elimination methods, I'll just do Gauss and LU decomposition. They are twice as fast. So that's what I'm saying, not that much better. They only reduce by half, which sounds like a lot, like half sounds like a lot, but we need to be by orders of magnitude to be making a difference. If you've ever used Gauss-Jordan, it's basically the same as inverse. It's between the inverse and the elimination. So what about an iterative method? How many flops is that going to take? No one knows. It's impossible to know, right? It's like, who knows? It depends on your guess. So better. It's always better. Otherwise, we wouldn't use it. So the nice thing is when you're using this in real systems, like real engineering systems, we have good guesses, and so it's not so bad, okay? If it was, then we wouldn't use them and we would use a direct method. You have a question?
If you had a single like multiplication, but they were really big numbers, could you have just that one multiplication take up more than one flop?
No. It doesn't take up more than one
It was,
flop.
bigger than 64.
No, computers, they don't care. Yeah. Yeah, any other questions? So go home, talk about the flops to your friends. Linear algebra.
Remember when you were talking about if statements?
Yeah.
And somebody asked if that's how 20 questions worked. You
Oh,
said
yeah,
you hadn't
yeah.
played it before.
Oh,
There you
gosh.
go. You can like show it to your son or something and explain to him for loops. You like turn it on somehow. I don't even know how to turn it on. Oh, here we go.
Okay, sounds good.
But then there's backlight. And it asks you 20 questions.
So you got to think about something.
Oh, right.
Yeah.
Wait, what the heck is this going to do? Guess it?
Yeah.
It tells you
It's
what
going
it
to tell
is.
you what you're
Okay.
thinking of.
It's like potato.
I'm ready. I have a thing.
So
what do
it
I
should
press?
ask a question.
It says ready. What do I
Say
press?
yeah.
Oh, yes. Okay, got it.
Did it work?
Nope, it's not an animal. Yeah. Oh, shoot. I answered it wrong already.
That's okay.
Think of a new thing that fits in your head.
Okay. No?
You just gotta wait 18 more questions.
How does this have this much information?
I don't know, but it works.
It literally guesses correct every single time.
But what if I said something weird like
Gauss-Jordan
Like-
elimination.
no, but like
Played with it.
what if I said like a French press? Like would it get that?
I don't
What?
A French press, like a coffee maker, like a
Yeah.
French press coffee
Oh,
maker?
it would probably say like a coffee maker.
Does that
Or a
count?
press.
It's gonna get it. I picked tomato. Like it's already
Yeah,
like
it's gonna.
Is
get
it red? Is it round? Is it
does it
smaller
smell
than your...
sweet?
Tomatoes
No. Right?
I don't think so.
You can say sometimes.
They smell like tomatoes. Usually you want to say yes or
unknown.
no.
Well, if you click yes every single time, it guesses a dog.
Okay, finish my questions for me.
For a
tomato.
tomato.
Yeah. I got most of them through. Other
Is
questions?
it soft? Tomatoes are soft.
Sometimes. Sometimes soft.
Matrix multiplication with a calculator.
Yes.
What
Does
does
it
the
roll?
REF?
That's row reduction.
So
Can't
how
make
is that
it
different than with
Look too easy.
Row reduction
Can I?
Oh,
is
it's
just one
teasing you
step
now.
of elimination. So
Does it
just
have
go in and look at, like if you
skin?
Google Gauss elimination, you'll see
it
the steps
bright?
of row reduction, and row reduction
I mean,
just
I
does
guess.
one step.
Okay.
So
Red,
Gauss
bright
elimination,
red,
it basically
yellow.
takes a row and
Is
it
it red?
reduces the row
It
to
knows.
one
It knows.
variable.
Does
makes
it
the other
taste
zero.
sweet?
So it-
I don't think tomatoes are sweet.
And so when you're row reducing,
Say
you want
something.
your bottom row to only have one unknown, the rest are
Is
zeros.
it larger
the row
than
above it, you
a
want two
pound of
unknowns and
butter?
one zero. So
Okay.
if you're doing it like
Pound of butter. Shannon, what does a pound of butter look